So we've talked about a binary dependent variable. Let's think about an ordered dependent variable. So we have a categorical variable, but there is a particular order to them. And because there is a particular order to them, we can think of it as a similar latent variable model, just with more than one threshold. So we had the threshold at 0 between category 0 and category 1. With the ordered probit, we have many thresholds. Here we call them tau. And they are the thresholds between the first and second category, the second and third category, the third and fourth category, and so forth. So we can have many categories, and because they're in an order, we can think of an underlying latent distribution, a continuous variable, that explains the observations in the various categories. So we predict y for a particular category to be 1 if the observation of if y star, the latent variable, is between the two thresholds. And we predict a 0 if it's not between the two thresholds. So if we think of ordered probit, then we still have a standard normal distribution for the latent variable, and we just have to estimate a few more of these threshold values. So in addition to estimating the beta coefficients, we now also need to estimate these tau variables. And of course we need to fix one, otherwise we could just move the intercept up and move all the taus with it. And then we always have the equally good predictions. So we have to either fix the intercept to 0, or we have to fix one of the taus to come up with one solution to the problem. And then the probability you can think of as cumulative normal distribution. So if you want to calculate the probability of being in the second category, you need to calculate the probability density up to the second category, and then up to and including the second category, and then the difference between those two is the probability of being in the second category, and that is your predicted probability. So in R we can use the polar function from the mass library to calculate the ordered probit, and you also see an example here of how to calculate predicted probabilities for a particular category. And just like with logistic regression and with probit, we can work out the probability density function for the dependent variable and work out the log likelihood function that we can then simplify and optimize to estimate beta and tau. When the dependent variable is categorical but not of a particular order, so it's a nominal variable, we cannot simply use probit, and we can't also really use this latent variable specification because you don't know, there is no particular order to them, so also not a particular point on a virtual or latent line. So instead we need to actually run it as if there are many different logistic regressions. We treat every category as a separate item to predict, and so you can think of it as a set of separate logistic regression, each with their own beta coefficients. The only constraint we have here that was not there if they are all separate regression is that the total probability needs to still be 1. So if we predict a 30% chance of being in category 1 and a 20% in category 2, and there are 3 categories, there can only be 50% chance that it is in the third category. So it's constrained in that sense. So we get separate regression equations with separate betas for each of the categories, and they are estimated under the constraint that the total probability has to add up to 1. And the package multinom in the neural nets package in R can estimate this. And again, we can work out the probability density function and the log likelihood function that we can use in Optimor, for example, to estimate the parameters.